speaker will be Dr. Alistair Hay. Alistair Hay is Professor of Environmental Toxicology at the University of Leeds. And as you know, for many years he's worked in issues related to chemical and biological warfare. He is also a contributor to a very important document produced by the World Health Organization in 2004. And that's the Public Health Response to Biological and Chemical Agents. And if you haven't seen that document, I would direct your attention to it. There's a lot of valuable information in there. So I'll pass the floor to Alistair Hay, who will speak to us about research and choices. What would you choose?
Madam Chair, Monsieur Chair, Mesdames et Messieurs, excusez-moi, en Angleterre, non parlez-vous français. I will try to speak slowly so that what I say is clear. The talk I am going to give is material that I have prepared for teaching, primarily for chemists, but also for biologists, and it is some case studies. Is it possible to put the lights down a little bit near the slide? This one here. This light can be switched, this one off. So I hope this session will be interactive. What I mean is I will ask you questions at some stage, and I hope people will give me answers. There are no right, there are no correct answers. I just would like some answers. But you have an exercise, first of all. For 10 seconds, I want you to think, what do you imagine a chemical plant looks like? Do you understand a chemical plant? Can you think what your idea of a chemical plant is? Like this? Yes? For many of you, this is a chemical plant. This is chemical industry. Did many people think of this one? 3, 4 people maybe think of this one. This is also a chemical plant. Like everybody around this table, we are all chemical plants. Our enzymes are breaking down the proteins and carbohydrates we have for our lunch to make small molecules and even smaller molecules. Your lunch is really just chemistry. This plant here is a plant that was used in Chinese medicine and still is. For thousands of years it is called ephedra. And it is used as a stimulant to make you more energetic. So for some people who feel in the morning when they get up, you know, they need something to move them, and the caffeine in the coffee is not going to do that, ephedra will help. And it has been used to make people feel better. It makes them feel more energetic, so they want to move. So if somebody is too heavy, perhaps, and they want to lose some weight, they can take ephedra. But they take too much. And so this chemical, it can be used well to help people, but it can also be used by too much. So if people take too much, it can cause heart problems with the heart and the respiratory tract, the lungs. So the United States Food and Drug Administration, it cautions people on how much you can use, and some of these products are restricted. So ephedra can be used well, and it can be used badly. Now I have a little chemistry for you. If you look at this molecule, it is called pseudoephedrine. It is related to ephedra from the plant. If you look at this hydroxyl group on the top of this molecule, you can change this hydroxyl group, and the OH becomes hydrogen. Pseudoephedrine is used in cough linctors. When you have a cough, it makes your chest easier. It is, they say, soothing. But if you want to make more money, and a lot more money, you can convert pseudoephedrine to methamphetamine. Methamphetamine, or crystal meth, as it is called, is a drug that is widely abused in Western Europe, in the United States. So, a little bit of pseudoephedrine, $1 worth of pseudoephedrine will maybe make $20 worth of methamphetamine. So you can become very rich very quickly. But this is an example of use of chemistry. I will not tell you the recipe, how to make this, but you can find it, not too difficult, too much difficulty. And it is a process called reduction. So one of the questions we pose to our students, we ask our students, is if you have a problem, if you know that you can make crystal meth, what information do you tell people? Do you tell parents that their children may be doing this when they say they're off playing baseball or gone to the movies? They might be making crystal meth. So one of the questions, and I want to give you an answer, we ask people is what information you should tell the public about this process. This slide here, this is an irrigation trench, a trench for water, for wastewater. It is in Tijuana, in Mexico. And what you see here is cartons, empty cartons of material that contained cough linctors. So the people who use this have taken the cough linctors to take the pseudoephedrine out of the cough linctors to make crystal meth. So maybe we should ban cough linctors, because cough linctors is the source of pseudoephedrine, which you can make crystal meth from. So maybe, should we do that? I will leave that question hanging in the air. Now, this is a teaching slide that I have prepared. And you will notice that there are two axes, non-intentional to intentional, moving from error to criminal. In the laboratory, we're used to making the wrong observations. We might mistake a 5 for an 8. We wrote something down very quickly and we misread it. And we transcribe the wrong letter, the wrong number. Now that is a simple mistake. It is an error. We should maybe be more careful, but it is not something that we need to go to jail for. Sometimes we may do the wrong analysis. We want to separate two chemicals. We use a chromatography system. Perhaps we use one solvent to separate some chemicals, and it doesn't do this. And we get one single peak, and we say, that peak is substance A. But maybe it's substance B, because A and B move the same way in this solvent. Maybe if we used a different solvent, we could separate them. So we can do the wrong analysis. And that wrong analysis may be because we should have read the literature more, we should have looked at more publications to find better solvents to separate, or we simply just didn't know. So it could be a mistake. Your supervisor may be cross with you, but it is part of the learning process. Conflicts of interest. Maybe we do research for, say, a drug company, a pharmaceutical company. It is important to tell people that you have had money from somebody to do a piece of work. We say that it is important to declare that you may have an interest. The work that you do may have a commercial interest. Now, we are scientists. We are curious. We want to know about the world. We are young postgraduate students, young doctoral students. We're working in a chemistry laboratory, and somebody says, Alistair, did you know that you can make crystal meth from pseudoephedrine? This process that I showed you before. Do you know that you can do that? So you are a young chemist. Would you make it? Shibril, would you make it? Would you be curious enough?
Well, actually, I really concentrate on what is the benefit of that. If it's good for public welfare, I will go for it. But in this case, I don't.
So if you were a starving student, you were short of money, and you could make some methamphetamine, and you had to pay your college, your university fees, would you be tempted to make some?
For the time being, I don't. But I don't know when I was a student what I behave.
So, but would you be curious as a chemist that this is a simple process? Would you be even tempted not to make some to use, but just to see whether it was possible to make it? Would you be interested to try?
It is interesting, actually, yes.
You'd be curious, yes.
Yeah, it's interesting.
And that's what we are about as scientists.
Yeah.
We're curious.
Who's asking? That may make the difference. Who's asking the question?
Oh, no. This is for you to decide. Would you do it? You're working in the laboratory. You've heard about this. Would you be tempted to do it?
As a scientist, I
No.
will do it. I'm curious on science. I want to know what's how to do it.
Science attracts people with curiosity.
Okay, so we established that you might be tempted just to see whether it's possible.
Education is part of life.
So, you make it. Now, I mean, when we get findings in the laboratory, the first time we find something that's new and exciting, we're so stimulated, we're excited about the finding. But could it be the way we did our experiment? We all know that science is about reproducibility, yes? You do something, but you have to be able to show that you can do it again. That it is just not a one-off finding. Other people have to be able to reproduce what you've done. So, would you make it again? Would you be tempted to try and make it again? You've done it once. Were you lucky? Would you do it again?
In this case, it's going to be quite ethical question here.
Right.
I mean, somebody is conscious, I don't think he's going to do it. I'll speak for myself. I satisfied my curiosity and I saw the outcome, and it's going to be illegal thing that do it again for maybe to get some money from it or some benefits. It's going to be quite ethical.
Yes, because your laboratory will probably not have a license to have this drug.
Absolutely.
And it's an illegal drug.
Sure.
So making it again, you have to have made a conscious decision.
Sure.
But, so, say you can make it again, would you, if you did make it the first time, I forgot to ask this, would you tell somebody about it that you'd made it? Or would you keep that information to yourself? Would you boast about it?
It's a science. I will pass it to somebody else.
You would. And then somebody says to you, do you realize that you have made this drug, which is illegal, and we are not allowed to have it in our laboratory? So even though you were curious,
Yeah. We are in a position of teaching. So,
Okay.
yeah, so we teach somebody else how to do.
and you're
But I inform him the risk of it.
so you have made it, would your students be tempted to reproduce it, do you think?
It does depend on the, it's individual dependence. But as information, I pass it. That's my job,
Okay.
passing information.
So you pass on information,
Yeah.
how to make methamphetamine from cigarette.
Yeah.
So you make it again. Having made it again, then it may be probably very different in Tripoli, but perhaps in London, some student, Alistair, me, a friend, he comes to me and he says to me, Alistair, I have a party. I have some friends coming to a party next week. I hear that you have made some methamphetamine. If you can let me have some, if you can sell some to me, it will make my party really good. So will you sell some to me? Would you? You notice then that if you sell some, that you're moving across this from error to something that is more criminal, and from non-intentional to intentional. So if you then sell some, you sell a little bit, well, why just leave it as a little bit?
Doctor, I'm really starting to get uncomfortable with these decisions here. I think it's time for me to destroy it and never admit to having ever done that before.
You'll never end up in jail then. Hopefully not from a chemistry laboratory anyway. So,
I think we need to give some work to the lawyers to make some legislation or regulation regarding this. But as a scientist, that's the research is about. See, is to satisfy your curiosity, publish it, article, publication, make everyone knows. Let the legislation decide if it must be regulated or not.
I would tell people that this is not just a made-up story. There have been different scientists who have done this and that have gone down this road. So it's a learning exercise, if you like, for our students. What you want to do, what I want to do, sometimes I can just use this slide for 1 hour and I make them give me answers. I want them to think about the issues. I have just got time then to do one other biological case study. I think I have maybe 15 minutes left, yes? Okay. I have used different headings. these can be changed. So the first question for your biologists is about disease eradication. We all want to get rid of disease, yes? I mean, unless we are working for a biological weapons laboratory, most of us want to eradicate disease, yes? So it is important to understand the disease. Yes, would you say it is? So understand how it is transmitted or passed from one person to another. So we find out about the transmission routes, and this is crucial to understand about disease. You would say that you want to know whether it's a bacteria or a virus, which kind, yes? You would want to do that. This would all be important. If you want to, disease is spread by person to person, you want to limit that, you want to stop the spread, you control infections, yes? You want to learn how you control infections, yes, would you say? That would be important to know how you prevent the disease spreading. Infection control, okay. So we have infection control. What about understanding what it is about the disease that causes the problem? So if it's anthrax, do we want to know how the organism operates when it is in the body? We want to control it at some point maybe, because we want to eradicate disease and we want to stop infections. So understanding the way the organism works is important, yes? The mechanisms, okay. So we understand those. What about developing methods for treating the disease? Vaccines, for example, yes? Would you say that if it was a disease like polio or smallpox, if we can develop a vaccine, it would be important to do that, to eradicate it? Okay. Now, when you develop a vaccine, or you may be trying to produce some antibodies, you want those antibodies to identify your agent very well, yes? Because it's the more the glove fits on the hand, the more the antibody binds to the organism, the better, yes? Because it's going to be more effective. So if you can produce your molecule to better design a vaccine, that would surely help, wouldn't it? It's better to have the hand like this to then fit the glove to the hand. Because if I say, give me a glove, you will say, but how big is your hand? Have you got 3 fingers or 5, or do you have 2 thumbs? I need to see your hand to make it work, yes? So understanding what constitutes the organism is important. So understanding its genetic makeup would be important, would you say? Because it's the genes that determine my hand. So would you say it was important to understand the gene sequence of the organism or not? Jamal is looking dubious. He is wondering what elephant trap I have set for him.
For raising or for creating an immune or measles, so you don't need to know the molecular of the cell if you want to raise an antibody.
You,
Or if you want to raise immunization, you don't need to know the antibody. To know the cell membrane and the molecular biology of the organism.
but if you want to understand maybe a component of that, and you want to try and modify
You can
it,
raise the immune without knowing the molecular biology of the organism.
so you wouldn't be interested in understanding
No,
the
not
genetic
really.
sequence.
That's probably another side or another matter of the.
But this is all part of, so I'm also thinking about not just virus, but bacteria, and how you might control some of these. So at what point would you be interested in understanding the gene sequence of the organism? Is there a point where you think the gene sequence is important to understand?
Absolutely. Let's take, for example, drug resistance to antibiotics. We need to understand the gene sequence, where the mutation happened, so we can identify the right treatment for that resistance.
Right. So you would, the gene sequence is important, so you would want to know to determine the genome. Right.
There's another aspect, it's also from the epidemiologic aspect. You can actually determine the origin of a strain of bacteria or even viruses if you have a genomic clone, a bank of genes. You can compare it with with your database and tell that this strain is from Africa or Asia or so.
And this is what they're trying to do with H1N1, to look at the phylogeny of it. Yeah. Right. Now, what about if you have a virus and you understand the sequence, how would you feel about reconstructing a virus genome? And we had this with Tatiana this morning when she was talking about H5N1. So a little bit of what I'm going to talk about now has already been stolen from me by Tatiana. But I can forgive her in this instance. She didn't know what I was going to talk about. So this is just for illustrative purposes of teaching. So you can ask students whether they would synthesize the polio virus. And this has been done. It has been done chemically using available nucleotide sequences. There was controversy when it was done, but the argument for it is to understand the sequence, to look at how folding occurs, where mutations may have arisen within the polio nucleotides, and also to look at differences between different strains. So you can also ask whether somebody, having made the polio virus, would be interested in making smallpox. So this is a question to push the students with. I won't push you all here now. Reconstructing the 1980 flu virus, which has been done. And then, of course, human endogenous retroviruses, yes, of which there are many. 80% of our genome is probably comprised of retroviruses that our ancestors have been exposed to over the years. So this is an example of teaching sequence, and I have others on antibiotic resistance and different other disease pathways. So what I'm trying to show you here is that it is possible to frame, if you have a question, it is possible to frame it, to construct it in a way that you can use to force your students to engage with you, to answer questions. And it's more interesting teaching, but it is also a way of making them think. And that point I will stop. Thank you.